This webcast discusses Ohm's law. So if you have a piece of wire or some conductor and there is no voltage difference applied across the ends of it. So let's say that, perhaps your calculator charger sitting on the table, it's not plugged in to the wall, so there's no delta V on it. The free electrons in that piece of wire are always moving, but they have a very chaotic and random motion. And this is depicted in this top picture here. The yellow box is supposed to represent a piece of wire that's been blown up thousands and thousands of times. The red circles are the atoms, which are rigidly bonded to each other. They are not moving. But then the little green circles represent the electrons. And you can see the electrons here. Some of them are moving to the right, some to the left, and up and down and at angles, just in all different directions. This is just because of the normal thermal energy of the electrons. They are free to move, and they just move around in all directions. But because of the random nature of their motion, there is not a net flow of electrons, coming in from the left and moving through this piece of wire and moving out on the right. They're just kind of moving around the general area where they exist. Now contrast that to the picture at the bottom, where we can see that all of the electrons are moving in the same direction. The reason they're doing this is because now a battery has been connected to this piece of wire. This symbol here with the minus and plus signs representing the negative and positive terminals of the battery, that represents a battery. And then we've got a circuit of wires, and so there is a voltage difference applied across the ends of the wire. That voltage difference creates an electric field that applies a force on every charge and makes them move in the same direction. Now they are moving in such a way that you are getting a bulk flow of charge, a net flow of charge. If we were to draw a line at some point along this wire, we could count the number of electrons moving past that point in the wire. And so we have a useful electric current. This velocity, when the electrons are moving in the same direction, is called the drift velocity. And they're just regularly, when that electric field gets applied, because of the voltage difference that's applied on both sides of the wire, the field starts pushing, it gets distributed around the circuit almost at the speed of light. And I want to caution you, electrons are not flowing out of the battery. The battery provides the electric field that starts pushing the electrons in one direction. But the electrons are already in the wire, right? They're already all the way around the circuit because the entire circuit is made up of atoms, and there are protons and electrons in every part of the circuit. So at the point where they are, the electrons start to move in one direction. So a delta V, a voltage difference, is required to sustain a current. And so you have to maintain that voltage difference while the circuit is working. And typically for the circuits that we are going to look at, we will have that delta V provided by something like a battery. Okay, so the battery is providing the energy that is driving our circuit. Now, the amount of current that flows through the circuit depends not only on that voltage difference, but also on the resistance in the circuit. So there are components in the circuit which help to resist the flow of the electrons. And a general term for this is a resistor. It's any electric component that puts up some resistance to the flow of current. And sometimes these resistors are chosen purposefully because they can help to regulate or control how much current flows through the circuit. The resistance of a resistor is constant, and the amount of resistance is measured in units of ohms, OHM. The symbol for ohm is the Greek letter omega, which looks, a little bit like an upside down horseshoe. And so that is the symbol for ohm, which is the unit of measure for resistance. When we're talking about resistance, we usually represent it by the letter R, which is an uppercase R. Okay, so the current that flows through a circuit depends not only on the voltage difference across the ends of the circuit, but also on the resistance of the circuit. And so here is a relationship called Ohm's law, and it tells us that the current is proportional to the voltage difference, and it's inversely proportional to the resistance of the circuit. So here, current is measured in amps, the voltage difference is measured in volts, and the resistance is measured in ohms. So I equals delta V divided by R. Since there are three variables in this relationship, a useful mnemonic tool to using this law is called Ohm's triangle. And if you could keep this picture in your mind, it's really helpful, because we have many reasons to use this relationship, but sometimes we want to find the voltage, sometimes we want to find the current, sometimes we want to find the resistance. And so if you can keep this triangle in mind, when you cover up the variable that you want to solve for, it shows you the equation that you need to use. So for example, if I want to find the voltage difference, I cover up the V and I see I have I and R on the same level. So delta V equals IR, current times resistance. Let's say I want to solve for resistance. I cover up the R, and then I see I have V over the I. So the resistance equals the voltage difference divided by the current. So here, in this example, I have a resistor, which is, set in a circuit. Someone has measured the voltage both at the beginning of the resistor and at the end, and the difference in voltage is 5 volts. The current coming through is 0.05 amps, and we'd like to find the resistance. Well, R would be the delta V divided by the I, and so then I would plug in and I would find that the resistance is 100 ohms. Let's go work a few additional problems using Ohm's law. So I'm going to go to worksheet 8B. I'm sorry, worksheet 9A, and I'm going to go to problem 4. So when you are dry, your body has a resistance of 980,000 ohms, but when you're wet, your body's resistance is much smaller, only 1,000 ohms. So we want to find out how much current would flow through your body if you touched a live wire of a 120 volt circuit when you're dry. Okay, so I'm going to get that picture in my mind of Ohm's triangle. And since I'm trying to solve for current, I'm going to use the equation current equals the delta V divided by the resistance. And here the delta V is 120 volts, and the resistance when I'm dry is 980,000 ohms. And so when I do this, I get 1.22 e to the negative 4th amps, or 0.000122 amps. Okay, this is when I'm dry. When I'm wet, the resistance is much smaller, so the current would be that 120 volts divided by just 1,000 ohms, and so I'd get 0.12 amps. So if we compare these two numbers, 1,000 times more current flows through your body when you are wet. And that's because the resistance is so much smaller. So resistance sometimes is a good thing. It can be used to regulate or control how much current flows through a circuit. And so just like, your body might become electrocuted if you touched 120 volts when you were wet, well, in a circuit with a light bulb or some other component, that light bulb might rupture if too much current flows through it. And so you might want to choose the amount of resistance in the circuit to make sure that doesn't happen. Let's do one more. Here, a resistor has a potential difference of 5.65 volts applied across it and a current of 345 milliamps. I'm just going to make sure I pay attention to the milli there, and we want to find the resistance. So when I look at Ohm's triangle and I cover up resistance, resistance would be the delta V over the I. And so the delta V here is the 5.65 volts, and the current is 345 milliamps. I need to, make sure I use amps, so I'm going to say that's 345 e to the negative 3 amps. And so if we do that math, there's a resistance of 16.377 ohms.